Hello and welcome. This is part 2 of rotational motion videos. In this video, I'm going to show you how to calculate the moment of inertia for various mass distributions. Let's start with the formula for point particles from number 1 to n, and each is mi of mass mi and ri away from some rotational axis. So its square appears in the formula. So that's our basic formula for distribution of point particles. And then I'm going to show you a couple of examples regarding continuous mass distributions where we simply replace the summation with an integral. So it's going to look like this: dm r squared, and this is over some volume or whatever the object is, the dimensions of the object. So let's start with really simple examples, let's say a massless rod and two masses attached to the ends of the rod, and there's this axis here. Okay, the first mass is m1, which is r away from the axis of rotation, and the length of the rod is L. The second mass is m2. So the rod itself is of negligible mass. Compared to m1 and m2, it's negligible. So let's ignore that part for now, but let's find the moment of inertia for this mass distribution, which is just two masses. Basically, you plug them in in the summation. So the moment of inertia will be the first mass times r squared, plus you'll need, of course, this distance, which becomes L minus R. So m2 times L minus R squared. Okay, so that's it. Just two terms. Now, what if you have a distribution which is made of four particles? Let's say at the corners of a square, you have 2, 3, and 4 masses. And let's say these are all equal, m. Just make it easy. M, 4 equal masses, and the side is A. Okay, it's a square. It's a square. So what will be the moment of inertia for this distribution? Let's change the axes now, okay? Let's think of a couple of options here. Let's say there's one axis that goes through the center. So the rotation, okay, I didn't mean that. So that the rotation, okay, what's going on here? The rotation is about this axis. And then let's pick this one here. Let's name these 1 and 2. Okay, and then 1 here. Well, these axes are all on the same plane as the square, okay? 1, 2, 3, and maybe a diagonal 1. A diagonal 1, and this is axis number 4. Okay, it's going through the center. Doesn't look like it, but it is supposed to go through the center. And finally, let's pick an axis that goes through the center again, but it's perpendicular to the plane of the masses. So I'm just going to denote it with a dot and a circle. Okay, this is number 5. So we're talking about rotations of the system like this, or maybe the other way around. Put the arrow on the other side. Okay, I mean counterclockwise rotation. So that's number 5. So I1, I2, I3, and I4 need to be calculated. Okay, The method is exactly the same. It's the individual masses times, the square of the distance between the masses and the axis of rotation. So let's start with I1 here. So I1, this axis. Okay, we have 4 masses, and each of them is half of A away from the axis. This is A over 2, and the same applies to the other 3 as well. So we have 4 times, because we have 4 of them, and each will contribute the same way, M times A over 2 squared. Okay, so 2 squared is 4, ma squared. That's what the moment of inertia for 1 is. Okay, each will contribute as m times a squared over 4, and we have 4 of them, so ma squared is the total. What about I2? I2, for I2, since these are point masses, the one on the right top corner and the right bottom corner, those 2 masses will not contribute to the moment of inertia because they are on the axis. Instead, we'll have to consider the other 2. So ma squared, this will be from the top left corner, this one. And we have another one right below it. So there are 2 of them, 2 ma squared. 2 ma squared. What about I3? I3. Now 3 is horizontal, but if you think about it, it's not different from axis 1 due to symmetry. So answer is the same as I1 ma squared. 4 masses contribute ma squared over 4, so the answer is ma squared. Now what about 4? Now 4 will have 2 terms again, because the diagonal ones along the axis will not contribute. The other 2 will, and I just need to find the distance between those masses and the center, okay, or the axis, I mean, okay. So there's a right triangle there. Okay, this is half of A, so is this one. Right, and then using the Pythagorean theorem, we'll have A squared over 4 plus A squared over 4. Take the square root of that. Well, you have 1 over 2 A, right? So you will have here square root of A squared over 2. So A over square root 2 is this hypotenuse. And we're going to square that, which will give us A squared over 2. That's from one of the masses. M times the square of A over square root 2. And we have 2 of these. There's another one on the other side, so multiply by 2. Okay, so A squared over 2, 2's cancel. Okay, is that really the case? A squared over 2, is this really ma squared? Let me double check again. This is A over 2 squared. A squared over 4 plus A squared over 4, 2A squared over 4, which is A squared over 2. Take the square root, A over square root 2. Okay, and then you square that, which is A squared over 2. And you have 2 of those, ma squared. Okay. And then for I5, we have all four masses contribute this way. So just add two more, and then you get to a squared. So these are the moment of inertia for this setting. Okay, so how about some mass distributions? All right. Now from point particles, now we move on to continuous mass distributions. All right. Let's start with really basic ones, like a thin rod of length L and negligible thickness or radius. Okay, so don't worry about that dimension there. So let's put the axis right here on one side, and suppose it's going to rotate around that axis. So what will be the moment of inertia of the mass M rod? All right. So since we gotta use a differential idea for infinitesimal, I mean, for moment of inertia, we consider an infinitesimal mass. Let's first of all, let's put this along an axis. Let's say x-axis, and then consider a really tiny cross section, a very small volume along that rod, and dm will be the mass of that section, which is x away from the rotation. So if I can write what dm is, I just need to multiply it by the distance squared from the axis and integrate it, and this will give me the moment of inertia. And x varies from 0, x equals 0 to x equals L. So the integration will be from 0 to L. So what is the m? Now, if this is a uniform mass distribution, dm will be equal to some density times the thickness of that infinitesimal pillbox, right? Very small section. So the density is what we need here. And since I'm ignoring the thickness, let this be a linear mass density. A linear mass density, which is just m over total length, is needed here. This is coordinate independent. It's a uniform and also continuous mass distribution. Okay, so if I multiply this lambda by the thickness along the x direction, I mean, not the other way. So this is just dx, infinitesimally thick section. I get dm. So dm is just this density, linear mass density, linear mass density. So I multiply it by dx, that is dm. And there's also x squared here, all right? And integrate it from 0 to L. So the integral of x squared is x cubed over 3 from 0 to L. So the moment of inertia for this setup here is 1/3 ml squared. All right, so let's try this for the same rod, but let's put the axis somewhere else. Let's say in the middle. What if I put the axis in the middle? Now this is point x equals L over 2, and this is the left end, which is negative L over 2. That's x. So around this axis, okay, so rotations like this, rotations like that. I'm I'm not going to calculate dm again, it's the same. What changes? What changed? It's the limits that change. So from x equals negative L over 2 to L over 2, M over L times x squared dx. All right, so M over 3L. Now I have x cubed. The upper limit is L cubed over 8, right? Over 8. Minus the lower limit. Now the cube of negative L over 2 is negative L cubed over 8. Two negatives make positive, so L3 over 8. So this becomes 2 over 8, or 1 over 4. 4 times 3, 12. So 1 over 12 ml squared. Okay, so the moment of inertia is the smallest if the axis goes through the center. And it's the greatest if it is going through one end. And these two are related. If you remember the parallel axes theorem from the previous lecture, from the previous video, and recognize the second one here as center of mass moment of inertia. Applying the parallel axis theorem, this I from the edge will be equal to I center of mass plus the mass of the rod times L over 2 squared, because that's the distance between the two axes. All right. Okay, you can check this. I mean, you can check this. Let's take a look at the right-hand side. ICM is 1 over 12 ml squared plus ml squared over 4. Okay, so multiply this by 3 plus 1, 4 ml squared over 12, which is a third ml squared. All right, so let me open up a new whiteboard. Let's do some mass distributions, continuous mass distributions. Let's continue. Other than the rod, how about a disk? All right. I think without proof, I told you that the moment of inertia of a solid disk would be 1/2 mr squared if the disk has a radius r. And the rotation is about this axis that goes through the center of mass. It's a uniform distribution. All right, so how do we find this? Using the formula we have, I equals dm r squared. Now the little r here corresponds to the distance between the axis and some infinitesimal mass dm. Why don't we take that dm to be a ring around that axis? That's one option, but this works because I know that the moment of inertia for that blue part only, which is of radius r, and some mass m. Okay, so the mass contained here is dm, right? dm. So if I just multiply dm by r squared. That is the moment of inertia of that infinitesimal mass. I just need to integrate it, right? I mean, I just need to integrate it from r equals 0 to capital R. So let's call the total mass just m, or how about capital M, right? Capital M. So the dm, the mass contained in that ring, let's find that. The mass contained in that ring will be equal to an area density, which I will denote by sigma, times two pi r times, actually it's area density is sigma, right? So let me just multiply it by r times d theta, which would be this part only. Let me show it to you with red. This much, very tiny. That corresponds to an arc length equal to r d theta. And then it will also have a thickness in the radial direction, which is simply dr. Okay, and the sigma is total mass divided by total area, pi r squared. So this will be m d theta dr over pi r squared for that little part, dm. And in my case, I want to find the mass of the ring. Let's call it the dm prime. Dm prime. So what do? I multiply this by the circumference, which corresponds to an integration on theta from 0 to 2 pi. Let's say this times the circumference. Okay, so I get 2 pi times m over pi r squared dr. And there's an r here, which I forgot to put. So let me just put an r here. Okay, so this will give me, pi's go away. This will give me 2 mr dr over r squared. So the moment of inertia then is found by taking into account all these rings, concentric rings around the rotational axis. So I will integrate over dr right now. So 2 mr over r squared times r squared, which makes this r cubed dr. So now I have 2m from 0 to capital R, 2m over r squared, this is the constant, times r to the 4th over 4, r to the 4th over 4, that's the integral from 0 to r, which makes 1/2 m r to the power 2, 1/2 mr squared. All right, that's the disk. Now, for a cylinder, it'll be the same, because any mass you would add along the axis of rotation will not contribute to the form, only add to the mass. So 1/2 mr squared for a cylinder. Now, what if I had a disk with inner and outer radii like this? So, okay. And make it a cylinder if you like. Why not? You know, it won't have any effect. All right, so let the inner radius be A, outer radius be B. Now the integration will be from A to B. That's one difference. And okay, let's find sigma. Do you mind if I call it rho this time? Because it's a volume density. And then you'll see why the height of the cylinder doesn't matter. The total mass is still m. So the volume density will be the total mass divided by total volume. And the volume is actually one cylinder inside another cylinder. Okay, we're talking about the mass contained in this shell here. I'm going to shade it with green. All this mass. Okay, so the volume of a cylinder is base area times height. So we have pi b squared. And then we subtract pi a squared from that and multiply that difference by L. That is our volume density. Okay, so you multiply this volume density by using the same method here. You take a infinitesimal mass, which is at radius r, let's say, okay? So this will have a thickness of dr equal to dr, that shell. And then you expand that from A to B. That's how you evaluate your integral. That's how the integral over the volume works. So let's write the, let's do the same approach, mass for this part. Okay, so you take this density, and that density has to be multiplied by the circumference, which is 2 pi r, and also the height, L. Okay, so this gives you dm, and then this has to be multiplied by another r squared, so you get the integrand. All right, so that's right. M over, let's factor pi and L. So we have b squared minus a squared here. The integral will be from 0 to, not 0, I'm sorry, from a to b, from r equals a to r equals b. In the m, we have rho and 2 pi r. Let's write 2 pi r and L here. Now you're going to multiply it by r squared, right? That's in the formula. So it makes r cubed. I forgot to include dr here. This dr goes there, dr. All right, okay, so that's our integral. Let's find the integral and get rid of L's and pi's. Okay, so this is equal to 2m over b squared minus a squared in the denominator. The integral will give you r to the 4th power over 4. Okay, the limits are A and B. So I is equal to 2m divided by b squared minus a squared. Now, 1 over 4, of course, is 1 over 4. Now I need here b to the 4th minus a to the 4th, which can be written as b squared minus a squared times b squared plus a squared. Right? If you multiply those, b to the 4th minus a to the 4th, but this cancels this. And the 2 goes away with the 2 here. So the answer will be, again, 1/2 m, but b squared plus a squared here, or a squared plus b squared. Okay, so that is for this shape with inner and outer radii. 1/2 m, a squared plus b squared. Okay. All right, so how about a sphere? How about a sphere? Let's clean this up. Okay, for a sphere, let's start with a hollow sphere. Hollow spherical shell of mass m and radius r. Okay, so a sphere, spherical shell of radius r. So the spinning is about this axis here. This is the center of the sphere. So let's take a look at a differential or infinitesimal mass again. How about a ring around the axis like this? All right, so this ring will be r away from the rotation axis, this r. And this r changes. If you move this around the surface of the sphere, r changes. But there's also the other r, which is the radius, right? The radius here, r. This is r, right? And let's call this angle here theta. So this makes r equal to capital R sine theta. All right. So the mass contained here, which is dm. What is dm? All right, now we have a spherical surface, and the area of that surface is 4 pi r squared. So if you divide the total mass by that number, you get the area density. Let's call it sigma, all right? The density, and it's a uniform distribution. But if I multiply that sigma by, okay, let's be careful here. Now I'm here, I'm gonna go along a, what we call a meridian. And I'm going to do that by changing theta a little bit by an amount d theta. So I get this side, an arc length along the meridian. I need that because I need to multiply it by a small increment like this along the ring. All right. Now that will be r sine theta, or capital R, let's say, the radius, times an angle, let's call it d phi. All right, so by phi, I mean, let's include an axis here. Let's call it x. And the projection, this is z. And x, y, z, there is y here, right? So I'm talking about the angle this makes with the x-axis, phi. So by doing that, this becomes my differential area element. And if I multiply it by the density, I get the mass contained in that area, right? So sigma times r squared sine theta d theta d phi. But the good thing is, if you rotate it around an axis, no matter what phi is, you'll have a symmetric distribution. So I could just integrate this over phi and get rid of the phi part already. So integrate this from 0 to 2 pi. That's for phi, okay? So you get, from the phi integral, you'll just get 2 pi. Okay, sigma is m over 4 pi r squared. And then there's another r squared here. Okay, and then sine theta d theta. All right. That is the mass. Two. So it is 1/2 sine theta d theta times m. Okay, so what I need to do now is to multiply this by the square of the distance, which is r. So 1/2 sine theta m times r, capital R, sine theta squared d theta. And the integral will be from 0 to, okay, here's the thing. Phi only changes between 0 and pi, okay? Not 2 pi. Be careful there. 0, pi, theta, and pi. Because you can always reach the other side using phi rotation. So this is only from 0 to pi. Okay, so we're integrating basically over now sine cubed. So the integrand this sine cubed theta. Here I have m r squared over 2 the integral of sine cubed theta d theta, which is sine squared times sine theta d theta. Okay, now sine squared is 1 minus cosine squared theta. So basically I have r squared over 2 the integral of sine theta d theta minus integral of cosine squared theta sine theta d theta. Okay, now the first integral will give me negative cosine theta. If I plug in the limits, This will give me negative, okay, cosine pi is -1 minus cosine 0, which is 1, 2. This gives me 2. Now the second integral. Okay, let's rewrite it as 0 to pi cosine squared theta. Let's take this negative sign here, okay, and then write it here, negative sine theta d theta, which is differential of cosine, right? So it's d cosine theta. So I'll get here cosine theta cubed over 3. This integral will be equal to cosine cubed theta over 3, and the limits are 0 to pi. Okay, but I'm adding this because I get rid of that negative here. So cosine pi is -1. -1 cubed is still -1. All right, and then cosine 0 is 1 minus 1 divided by 3. So -2/3. So this integral is, or the moment of inertia is, mr squared over 2 times 2, the first term, minus 2/3. All right, so 6 minus 2, 4/3. 4, 2, 2/3 mr squared for a hollow sphere. Okay, what about a solid sphere? What about a solid sphere? Now in that case, you're going to integrate over r as well. All right, let me leave that to you. Okay, let me leave that calculation to you. The answer will be 2/5. Solid sphere. This will be 2/5 mr squared. Okay, so make sure you integrate over the radial coordinate. You will have something like this. Integral of r to the 4th dr. Somewhere in the integral you will have that. That's where you get the 1/5 factor. Okay, so all right, let's finish here. Till next time.